optimizing biology or biological phosphorus removal. Before I get started, there's a few items, housekeeping items I'd like to start with. First off, my name is Greg Paul. I'll be the presenter today. The session should last around 45 minutes. We're muting all of the attendees' mics. We do this to avoid unwanted feedback. If you have any questions during the presentation, feel free to use the raise your hand button and we'll activate your mic. Or you may type in your question at the GoToMeeting panel on the right side of your screen. At the end of the presentation, then we'll go through the questions. I found that there's a lot of interest in this subject, and discussion on questions can sometimes take more time than what we have allotted. So what I'll do is probably save some of that information for the end of the presentation, and those that want to stick around after the presentation, we can go through those questions a little bit more in depth. If we don't get to all the written questions, I can also respond to those by email. With that, let's begin. Just a minute. Got a little glitch here. Okay. We're presented with a challenge of meeting low P limits or low phosphorus limits. EPA and state regulations are requiring these limits, but operators, as usual, always have challenges that they deal with every day. So this is not really going to be as big an issue as what people think, because we're always dealing with challenges. And operators tend to look at things from the perspective of common sense solutions, which end up being simple and economical. Okay. How we're going to approach this is we're going to, actually it went one too many. There we go. Okay, meeting those challenges. What we're going to do is 4 items. So we're going to look at how to evaluate and optimize your EBNR system, and then we're going to look at, we're going to do that by looking at EBNR fundamentals and the QLF tools that are available. And also we're going to look at real life applications using QLF tools. Then we'll end with trials and manufacturing delivering information. Evaluating and optimizing the EBNR system. First, check with your state regulatory agency. There's a lot of resources that some of them have, and some of those, the links to some of those resources are on QLF's webpage that's dedicated to wastewater under the resource section. The DNR, specifically in Wisconsin, provides a phosphorus operational evaluation optimization report worksheet. It looks like this. It's a list of items to consider when you're optimizing your treatment plant. Also, get as much training as you can on your system and work together with your engineering firm. Become familiar with phosphorus removal reference material. Again, the QLF website has PDF copies of a number of these reference materials, or links to where to purchase the manuals. Probably one of the more important things from what I've seen after being out in the field with a variety of operators across the country is it's really important to share information with other operators with similar type EBNR systems. What happens is a lot of times we as operators get to thinking that our system is unique. There's truth to that, but there is a lot of truth to the fact that there are a lot of similarities also when it comes to operating the systems. Another way to optimize your system is to test the EBNR system using what's called nutrient profiles to evaluate your the performance of the system and to see where improvements can be made. Gives you clues to where your problems are. Again, there's more information about profiles on our website. One of the manuals that we have online, EPA manuals, provides information and catalogs information on treatment plants that have already had to achieve low P limits. And that's this manual. It's Advanced Wastewater to Achieve Low Concentration Phosphorus. It's April 2007. A little bit old, but information is still pretty good. There's one quote in that manual that caught my eye. It says, facilities using EBNR, which is enhanced biological nutrient removal, significantly reduce the amount of phosphorus to be removed through the subsequent chemical addition and tertiary filtration process. This improves the efficiency of the tertiary process and can significantly reduce costs of chemicals used to remove phosphorus. This is actually taken from page 9 of that manual. In other words, what it's saying, having a EBNR system makes the overall phosphorus removal more efficient and reduce your costs. And dovetail to that is, if you know and understand how to run your EBNR system, it enables you to operate even more efficiently and reduce costs. So we're going to start going through the EBNR fundamentals and the QLF tools. First, QLF tools. I had mentioned it before. We got training and reference materials on the resource page. We also list a number of studies that have been done. Some are in the form of a short paper, or there's also a number of PowerPoint presentations on that page under the study section. Now the next part, and probably the most important part as far as what tools QLF can offer, is EnhanceBioPND. What the name really represents is we can enhance biological processes that remove phosphorus and nitrogen, both with the same product. What is EnhanceBioPND? It's a molasses-based product formulated to supplement carbon, minerals, nutrients, and biological growth factors. The product, when it comes to the BOD to nitrogen to phosphorus ratio, is 100, 4.2 to 0.5. The ideal is actually 100 to 5 to 1. So we're pretty close to ideal. We like to think of our product as a mock wastewater. How the product works. It's a well-designed product package of ingredients that, the main component is high carbon, but there's other components that help enhance fermentation. And when all of those components are fed together in an anaerobic or anoxic environment, it promotes a really good environment for what we call in situ fermentation. How EnhanceBio fits into the EBNR puzzle. There's 4 different things. We can improve the performance of the EBNR system. We can fill carbon gaps. We can improve primary sludge fermentation performance, and we can also provide carbon for denitrification. In the upper 2, what happens is when you use our product, you use less chemical and you produce less sludge. Now we're going to go through how our product interacts with the different fundamentals of a BNR system. Again, if you know and understand your BNR system, you can help improve its performance. I pulled out 7 what I consider fundamentals to a good operating BNR system. Cycling between anaerobic and aerobic and correct HRT or hydraulic retention time. The second is you need enough volatile fatty acids. Third, good anaerobic zone. Fourth, you need the right cations, pH, and temperature. You also need to operate with the proper SRT and return sludge rates. It's important to note where your oxygen's at, control that as you should, and minimize the impacts of dewatering and thickening within the plant. Okay, first one we're going to look at is the cycling of anaerobic, aerobic, and the correct HRT. Our product cannot overcome the issues that are related to incorrect detention times. If the detention time in a tank is slightly incorrect, we probably can overcome that. Our early indications show that, but that means you're going to need more product than what you would normally need if compared to if the detention time was correct. There's also designs and operating practices that can end up in secondary releases. In some cases, again, where they're minor, we can overcome that problem, but in major cases, not. Okay, you need enough volatile fatty acids. Well, EnhanceBioPND provides readily available COD, that's RBD COD, and the ingredients that encourage the production of volatile fatty acids within a good anaerobic zone. So this is where we really shine. We can provide as much volatile fatty acids as you need. So we can make up the difference. As far as one of the things that I found working with treatment plants over the course of the last year and a half is there's a thing that I call carbon overdose. You can actually overdose your system with carbon, either yourself by adding too much of our product, or if you are hit by a loading from an industry that has high COD. We'll talk a little bit more about this later in the presentation, but what happens is with a carbon overdose, you get a really good release of phosphorus in the anaerobic zone, but it takes 2 to 3 days to overcome or to get, to be able to get the bugs to recover that release. Good anaerobic zone. It appears that the better the anaerobic zone is, in other words, the less nitrates and oxygen that are coming into that zone, and the right detention time, those all create a good anaerobic zone. The better that anaerobic zone is, the better our product works, the less product it takes. We can overcome nitrates because that's how we denitrify in a system that has a total nitrogen limit, is we use our product to denitrify in an anaerobic or anoxic zone. And so we can overcome that, but again, it takes more product. So it's a matter of having either good operations or well-designed plants minimize the use of our product. There's an example of a treatment plant that I worked with in Virginia where it was a oxidation ditch. They had 3 rings, 3 separate rings. The outer ring was an anaerobic zone. What they did to improve the performance of their system, and what they were looking for was a better anoxic zone, mainly for denitrification, is they reduced the dissolved air or reduced the amount of movement or the amount that their brushes ran in that system. But the other thing they did is they eliminated their aerated grit chamber just ahead of the ditch, because that oxygen that was being entrained in the sewage coming into the ditch actually disimproved or made the performance of that anoxic zone less. So the other thing you have to watch out for is DO, at the tail end of the aeration tank being recycled back through the RAS into the anaerobic zone. We can overcome all these issues. Here's an example, a picture of a recycle flow from an aerobic zone to an anaerobic zone, and this is how you don't do it, because notice the air bubbles on top here. What you're doing is entraining a lot of air, and this is an anaerobic, supposed to be an anaerobic zone. Okay, number 4 of the fundamentals is you need the right cations, pH, and temperature. EnhanceBioP plus N helps with potassium and magnesium because it contains both of those. pH, our product cannot overcome pH issues or temperature issues. Number 5 is operating with the right SRT and return sludge flow rates. EnhanceBio will work as long as the SRT is within the proper operating ranges. If you get too low with your SRT, you won't get BioP to work. If you have too old a sludge, you actually have endogenous respiration or cell lyosin, and then you have phosphorus going back into your system, which is another secondary release, so to speak. And it gets a little bit more difficult for us to overcome that type of situation. But on the RAS part of it, I found a number of treatment plants where their return sludge flow rate was a little bit slow, and they had too much of a sludge blanket. And with that sludge blanket in the final clarifier, it caused secondary release. And EnhanceBio will not overcome that. In fact, it will make it worse because now you've got more carbon to release in your final clarifier. And adequate oxygen. With a conventional system, AO, A2O, and Barton flow, you look at the first zone, first aerobic zone, and the DO should be between 2 and 3 milligrams per liter. In extended aeration and oxidation ditch, high DO at the aerator and very low DO at the opposite end. Again, if you don't provide enough oxygen, we're not going to overcome that issue with our product. The last one is minimizing the impact of dewatering, thickening, or other recycle loads. And remember, those loads contain not only phosphorus, but they also contain nitrogen. A good way to take care of that is, if at all possible, is to equalize that recycle flow. We can overcome issues like this, but if you're thickening just for 3 hours a day, 5 days a week, there's a good chance you'd have to feed a lot of product to be able to overcome that, and that's fine. We can do that. But if you spread that out over the course of the day, then it ends up being less of a burden on your system, and our product is, you can use it more efficiently. And there's economic issues that you have to look at, when comparing our product to metal salts, and you may have issues of struvite control, so you have to take that into account. Okay, this is a video that shows, remember I talked about doing a profile. I'm going to do a quick description of a nutrient profile. This one is a P or phosphorus profile. On this graph on the left-hand side, it's ortho as P milligrams per liter. On the bottom is, the first one is primary effluent or influent into the system. The first 2 points are anaerobic zones. This happens to be Fort Atkinson. They have 2 anaerobic zones. Then they've got 3 aerobic zones after that. Up in the upper right, it's got the time of the day. These samples were taken and recorded, and you can see what happens when they turn on their belt press and send a lot of phosphorus through the system. Generally, if you look over here, this is 5 milligrams per liter. Generally, a system will normally have 5 to 10 milligrams per liter phosphorus on the influent side of their system. Watch what happens when, as time progresses during the day. You can see starting to rise, it jumps way up and then comes back down as the day progresses. Okay, and as always, toxic influence that would wipe out a BNR system. EnhanceBio is not going to fix a problem like that. It may help speed the recovery, though. We're going to look at the applications, real-life applications now. Lacrosse, we did a 2-month study where we fed continuous. It was about 10 gallons per million-gallon dose. And that's generally where we like to start our dosing when you're looking to improve the performance of a BPR system. But that's going to be relative to your BOD to phosphorus ratio. The lower that is, the higher this dosage rate is going to have to be. And vice versa, the higher this ratio is, the lower the dosage. EnhanceBioPND has, in this case, shown the ability to remove dissolved reactive P down to as low as 15 parts per billion. And in that 2-month study, it kept it at that rate very consistently. The range was 8 to 24 parts per billion during that time period. We sampled 3 days a week during the study. Okay, here's without and with EnhanceBioPND. Notice that statistics up above, the average total phosphorus is 0.87 and 0.44 here. In both cases, the flow is about 10 mgd. Here the dose was 86 gallons per day. Solids was pretty close. Now you look at the different components of phosphorus in the effluent. The blue is the phosphorus associated with the solids. The green is the ortho or the reactive or dissolved reactive phosphorus, and the red is non-reactive. You can see what happened is we really took the ortho level down to a minimum. I also did a quick calculation here just to give you an idea of how much the suspended solids can impact the phosphorus levels in the effluent. I look at total phosphorus. Let's say if your effluent TSS was 2 instead of the 9, we found that there is 0.035 milligrams of phosphorus per milligram of TSS. So we took that times 2 milligrams per liter TSS. That would give you 0.07 phosphorus associated with the TSS versus this up here, 0.316. And you add the reactive and non-reactive, you end up with almost a 0.2 compared to 0.44. So in this case, it was like about 50% of the phosphorus in the effluent is related to the solid. Okay, another application was where we used an automatic feed system. We also did this at City La Crosse. We fed the product only when it was needed. We did research on how to go about feeding the product when it's needed. In other words, we had to figure out a way to determine when we were lacking carbon, and we'll go through that in a little bit. We worked with City La Crosse and also ESA. They provided a chem scan for us to monitor inline the influent to our BNR system and the anaerobic zone of the EBNR system. We took those two measurements and we calculated what's called a P-release ratio, or PR2, and we found that PR2 actually tells you the health of the system or whether the system needs carbon or not. And I realize the type is extremely small on here. The purpose of this is to show you what the trends are at different points in time over a number of days. Again, this graph is set up similar to the other one that we looked at that was a video. There's the phosphorus on this side. Here there are points that samples were done. This is the influent to the system. These are the two anaerobic zones, and the last three are aerobic zones. Up in the right hand is the time of the day and the time of the day, roughly. In this case, what we did, and this was part of figuring out how to dose our product. What I did was actually sampled at the facility starting on Friday night. Actually, I started on Thursday, but I condensed the information to this one sheet. So I start here on Friday and go all the way through Tuesday, and every 12 hours show where this profile is at. Now, a healthy profile is going to show a healthy release here. Healthy release is anywhere from 2 to 3 times and more from the influent. So let's say the influent is 10. You'd want to see this at 20 or 30 for it to be healthy. In this case, I believe it's 6 there, so you'd want it to be 12 to 18. So this is a good release. And then right in the first zone with plenty of oxygen, it brings that orthol P level right back down to almost nothing, and it stays there through the rest of the system. So now, continuing with it, Saturday morning, you can see the carbon level drops off because, or this release drops off because the carbon level coming to the plant actually drops off. Same here. Saturday evening, the carbon is dropping off more. At La Crosse, they've got a brewery that slows its production on the weekend, and consequently, they end up with less carbon on the weekend. So then Sunday morning, you can see the release has really relaxed, and now, you know, the uptake. You look here on all of these, the uptake has been just fine, but now the uptake is starting to show signs of stress. And by Sunday evening, it's flatlined, and the uptake has really, you know, really got very poor. Now Monday morning, since the organisms are still in there that have the phosphorus, or the PAOs have phosphorus in them, when it gets the carbon load, it jumps this up right away, but it doesn't have the ability to take that phosphorus back in the aerobic zone. That's what I was talking about as far as a carbon overdose. Actually, what happens at treatment plants like La Crosse is where their industrial load drops way off on the weekend is that when the carbon comes in on Monday, the organisms aren't ready for it. They can do one portion of what they're supposed to. They can release well, but they can't uptake. But now Monday evening, they're already showing signs of recovering on the uptake end, and the release is even higher. Tuesday morning, the effluent's back to normal, but you can see it's still stressed here. By Tuesday evening, it's all back to normal. So in feeding our product automatically, what we're doing is looking at this release, and if the release isn't there, then we set up a control system to be able to adjust, to be able to bring that release on. This is a graph that shows there's three lines. Basically, there's the brown, which is the time-adjusted QLF pump speed. In other words, the feed pump speed. And it's time-adjusted. The reason it's time-adjusted is because the blue line is the effluent orthol P. There's an online orthol P meter at La Crosse's plant. And so that meter is 12 hours of detention time after the feed point. So that's why I time adjusted all of this. The green line is the PR2 that I was talking about, that ratio that determines when the pump should feed and when it should not feed. So here, the green line, as it dips down, the pump speeds up, and as it comes back up, the feed drops off. As it stays up here, it stays okay, but then as it starts dropping off, it starts picking up. Gets to its lowest point here, it's at its highest point, but then as it starts climbing again, this starts dropping off. And as this gradually drops off, this goes up. There is some operator control here. He found, as he was learning to operate this, that he made some adjustments. And so this is at a sharper angle for as far as how this drops. But you can see over on the left here, this is orthophosphate, which is the blue, and on the right, it's orthophosphate. On the left is the pump speed in the PR2. So you can see through the whole thing that the effluent stayed right where it should be, about a 0.15 ortho-P. Okay, augmenting a fermenter to improve volatile fatty acids production. Did that at Janesville, and we were able to achieve an average 0.13 milligram per liter total phosphorus. During that study and before, they measured your volatile fatty acids. From January 1st, from June, beginning of June until July, look at the variety of points for volatile fatty acids. The average is about 132 milligrams per liter. We started feeding 80 gallons per day. This is about a 12 to 13 mgd flow. Did 80 gallons per day, 40 gallons per fermenter. They got 2 fermenters, and we ended up with a 219 milligrams per liter of volatile fatty acids. That translated into more consistent effluent, full phosphorus in the effluent. And you can see this is from the first of the year until when we started. And there really isn't, this is probably the commonest point. Here it's not too bad, but you can see this time frame here, which is about a 2-month period. We had a couple spikes. This was a spike because we had a check valve that plugged in our trial setup. And so the pump was shut off for 2 days. Okay, filling the carbon gaps. When you look at filling a carbon gap, that's like when the industry shuts down over the weekend. Well, what we look at for dosing is about 10 to 20% of the pounds per day, pounds BOD per day deficiency. So let's say during the week you're getting, 1,000 pounds or 2,000 pounds of BOD a day. On the weekend you're getting 1,000. We would look at feeding somewhere between 100 to 200 pounds of BOD a day of our product. If your gap is going to be 3 days or longer, like an extended holiday, then we look at about a 50 to 60% dose rate, based on the product being at a 480 milligram per liter BOD level. We've done Fort Atkinson. They use the fill gap method. They do it at Christmas time and when industry shut down. La Crosse does it on weekends, and they do manually and automatic. You can use 4 pounds of BOD per gallon for doing calculations, and COD is about 7.8. Now, denitrification and improving the EBNR performance. Crew, Virginia, they were looking to denitrify, And when we fed our product to that, they found a side benefit. We were feeding 19 gallons per day to a 230,000 gallon per day plant. They found an additional 50% reduction in their ortho or reactive phosphorus. They went from a 0.33 to a 0.16, reducing the amount of alum they needed then. This is the plant that has no anaerobic zone, it's just an anoxic zone, and we still got BioP with that anoxic zone. The DO in that anoxic zone was less than 1 milligram per liter, and ORP was a negative 140 millivolts. We supply Crew since August of 2011 and King George County since January, and King George County now has 3 treatment plants that we're supplying. QLF will provide temporary tank and feed system at no charge for a 30-day trial. There's details on our website for that. Here's a picture of one of the temporary setups. We have a tank. Use a parasolic pump in this setup, calibration tube, and it's directly off the line. We use carrier water. We pump the product into carrier water, and that's discharged, in this case, right into the anaerobic zone. This is when we were at port, and here we were using a CPEX progressive cavity pump. Manufacturing, there's 12 plants across the U.S. There's a semi-delivery system across the U.S., for most of the U.S. Can carry loads 1,000 to about 4,000 gallons per delivery. The tankers are compartmentalized to about 1,000 gallons per compartment. So the minimum larger load is 1,000 gallons. Lead time is 2 days to 2 weeks, depending upon load size and location. And then totes are available. They're considerably more expensive because of the cost of the tote and the extra cost for shipping as well. Other products that we've done, QLF's manufacturing process is quite flexible. Crew, Virginia, has a zinc issue in their effluent, so they didn't want any zinc in the product, and part of our formulation includes zinc. So we keep the zinc out of Crew's product. Ripon, we're in the process of experimenting with a high nitrogen product, which would substitute for those that are using urea as a nutrient supplement. Well, I've hit the end of the presentation. If there's any questions, let me know. Any questions? Okay, if there are no questions, thank you very much and have a good day.